Okay. Look, I was saying that in general, we neglect resistant effects, يعني resistance of air and possible resistance due to يعني from the race on motion. Okay. هلا, this is why when we say it's moving at a constant speed, we consider that to maintain the speed, once I reach the speed, I can maintain it without additional effort from my engine. Okay. هلا, of course, this is an assumption ومنا مظبوط 100% because you will still have resistance of air, etc. But in this case, if you want, even if you developed a certain engine force just to oppose this resistance of air, ما حتأثر على التتا لأنه هول الفورسز حيكونوا along UT in a way that some of forces along UT is zero وما حتأثر على الكالكوليشن تبعنا. يعني even let's say if you have a friction developed along UT to oppose resistance of air, these two will cancel out. يعني these tangential forces will cancel out in a way to maintain constant speed. But because we neglect effect of resistance of air, we can consider that when we want to just maintain a constant speed, ما علينا نعمل a big effort from the engine then. Okay. What will happen to the effect of N at this inclination once the N projection on the path create a force pulling the... No, it will not create a force pulling the car downward. You know why? Because here you have change in direction. You remember that whenever we have a curved motion, you cannot have a curved motion without a normal acceleration. So N, the presence of your normal, will ensure the presence of a normal acceleration that will help you to change direction. Okay, so because if you don't have a N, you cannot rotate. So here the projection of N along UN will allow you to change direction and have a circular motion, and you will not move towards inward or outward. Okay. Yes. Tell me. If we change, look, if we change the value of theta, we can change then the value of speed. And here's the idea. If you want to maintain a constant speed for a certain radius, the angle should be related by theta equal tan minus 1 v square over rho g. If you change theta and you still want to ensure same same type of motion at constant velocity, then you should alter or your speed or your radius of curvature. If you want to move along the same circle, يعني if you maintain rho constant, okay, when you increase, you know that as you increase theta, tangent theta will increase. So if you want to increase the inclination, then you are designing based on larger velocities. So you should increase your speed in this case. If not, if you keep the same speed and same radius with this theta, you should have friction. You should rely on friction to have your circular motion, to be able to satisfy the equation sum of n equals MAN. Okay. Any other question? Okay. So this is a little bit a challenging problem, but it will help you to understand a lot UN, UT, UB frame. Okay. Another example is the design of ski. Okay. The design of the ski requires knowing the type of forces that will be exerted on the skier and his approximate trajectory. In the case as shown, determine the normal force and acceleration on the 600 Newton skier the instant he arrives at the end of jump A, where his velocity is 9 meters per second. So in this example, we have a ski problem. In this ski problem, they gave us the equation of the path trajectory, y function of x. They gave us the velocity of the skier when reaching point A. And they want us to calculate when we reach A, what will be the normal reaction acting on the skier, and also what will be the acceleration of the skier. Okay, so again, whenever you have y function of x, think about u and ut, because you can find the radius of curvature at any location of your motion. Okay, so here they can ask me to find the forces at any location. They selected in particular when I reach A. Okay, so my purpose is to find the acceleration of the skier and the normal acceleration on it when it will reach A. So let me first do an analysis on the forces acting on the skier at A. To start with, I have the weight, of course, and I have the normal reaction. Now, because I have in general, when you do ski, you can simulate ice as a smooth surface, unless they gave you a friction coefficient. Because they didn't talk about any friction coefficient for ice, this means that they are treating ice as a smooth surface, so no friction acting on your ski. So at point A, the only forces acting on the skier are the weight of the skier and the normal reaction on the skier. Okay, now in order to solve for this normal reaction, we need to apply Newton law. Okay, you can tell me why I don't use rectangular coordinates to solve for NA. Try it. If you want to write in rectangular coordinates, what you will write? You will write that if I consider this is x, as I did, this is x and this is y. Along y, I can apply to get NA. I will write sum of y equals MAY equals plus NA minus W. But how many unknowns do I have in this equation? I have two unknowns. I don't know the value of NA and I don't know the value of AY. So one equation will not be enough for me to solve for these two unknowns. And if I write along AX, I will not have any information about these, because if I write sum of x equal AX, all I can write that I don't have any force along x. So this means that AX is 0. So using rectangular components here will not allow me to solve my system, because here I don't have any idea about AY. I know that AY is dVy by dt, but do I know Vy function of time? No. If they gave me y function of t, then I will use this method, because if I have y function of t, I say if I derive the first time with respect to t, I get Vy, and if I derive a second time with respect to t, I get AY. But just I know y as a function of x, I don't have any relation with time. So this is why it's not an advantage to work in rectangular components here. However, if I use normal tangential coordinates, what is my advantage in normal tangential coordinates?
We will remove many unknowns.
Yes, because we know an. We know an is v square over rho, and the velocity at a is given. And the radius at A, we can find it because we have the function of the trajectory. Okay, this is why I will say the best choice here is to work in normal tangential coordinates. And then, yes.
Sorry, مش ال NA هو is just the normal, صح؟
ال NA مظبوط، ال NA هي normal at point A.
بس زمان كانوا يقولوا لنا إنه NA and W cancel each other. هل هالحكي مش مظبوط؟
No, okay. They tell you they cancel each other when you move on a straight line. Okay, but here A is the end of a curve, صح أو لا؟
Yes.
يعني look, now when you do the transition from the curve to the straight line, فجأة بتتغير النورمال. Just before reaching the straight line motion, your normal is larger than the weight. You know why? Because when you move on a curve, you have a n towards the center of curvature. A n here will have a positive value because you have a velocity and you have a radius of curvature. Now, when you suddenly move to the horizontal part, there is no more a radius. So the radius of curvature becomes infinity. For a straight line, the radius of curvature is infinity. This means that a n, which is v square over rho, becomes 0. And because a n becomes 0 on a straight line, because you only have the normal and the weight and no motion along y, then you can say that n and w will cancel each other. But this is not the case on when for a as a part of the curved path. Okay.
Thank you.
So n will undergo a sudden change when you move from the curved part to the straight part. N will be reduced because the value of n should be larger in the curved part, since you have to change direction and on the curved part. And when you move from this point to this one, you are still changing direction. So you have you should have a value for an, and an can be calculated as v square over rho. Okay, so now since my point of interest is a, at a I can consider what is ut, what is un. This is my path of motion. As usual, ut is tangent to the path. If I use this equation, ut is along the tangent line, and the tangent slope is given by dy over dx. If you derive dy by dx, you get that it's equal to 2 over 60 times x. So it's equal to x over 30. Okay. And now at a in particular, a is for x equal to 0. So we can say that dy by dx at point a is just equal to 0, because x of a is 0. Okay, this means that I have a horizontal slope and my tangent line is like this. This is my ut. Because ut is along v, I'm moving downward, so v is towards, at this point, v is towards the left, and this is my ut. Now, concerning my un, what is my plane of motion? I'm moving in the vertical plane here, and ut is horizontal, so un will be perpendicular to ut in the vertical direction. So this is my un. Now, at this point A, if I want to represent my forces, what are my forces? I have the weight and I have the normal. And of course, the normal will be larger than the weight, because I know that an will be upward. It will be towards the center of curvature. So now, once I put my forces and my frame, I'm ready to move to my equations. I can present UB here, but will I need to project along UB? UB, how is UB? UB is perpendicular to both UN and UT. So UB, yes, UB is perpendicular to the screen. But do I have any force perpendicular to the screen?
No.
No. So if I write sum of B equals 0, I will not get any relation, because already there is no forces along UB. So sum of B equals 0 will just give me that 0 is equal to 0, because I don't have any force along this direction. So here I don't need it. We say that when all forces acting on the particle are along the plane of motion, this means they are along UNUT plane, I don't need to write sum of B equals 0. However, if you go to the Formula 1 problem, in the Formula 1 problem, your path of motion was horizontal, but your weight is vertical, and your normal can be decomposed into a vertical and a horizontal component. This means that in the Formula 1 problem, you have forces along UB, But when you project them, their summation will be 0. Then you should use sum of b equals 0 because it will help you to relate your forces. However, when all forces are in the plane of motion, like this key problem here, then I don't need to use sum of b equals 0. It will not help me in anything. I can just use here sum of fn equals man and sum of ft equals mat. Now, at the particular point A, at A, I have that forces, I have the normal reaction already along UN and also the weight already along UN, but in the negative direction. So I can write that plus NA minus W equals to the mass of the skier, which is the weight of the skier over G. Here they are using G 9.81. In the exam, you can use it 10 for simplification, times AN. And this is the advantage of using normal tangential coordinates. I know the expression of AN. AN at point A is V squared over rho at A. Okay. Now, since they gave me already what is the velocity of the skier at A, I replace it. I still need to calculate what is the radius of curvature at A. And now I can use the formula we developed in chapter 12, that rho at A is equal to 1 plus the first derivative of y with respect to x at point A square, the whole term to the power 3 over 2 over the absolute value of the second derivative of y with respect to x. Here I already computed the first derivative function. The first derivative function is x over 30. So the second derivative is 1 over 30, which is a constant. Okay. So now I replace the first derivative at A by 0. I get 1. And I replace the second derivative by 1 over 30. So I get that rho at A is 30 meters because it's 1 over 30. So it's 30 meters. And now, once I replace rho, the only unknown in my equation is NA. I can calculate the value of NA. But in the problem, they didn't just ask for the normal reaction. They also asked for the acceleration of the skier at A. You know that the acceleration is divided into two components, AN and AT. Okay. For AN, I already did the calculation because I used it in sum of Fn equals MAN. And this is the value of AN. I still need to know what is AT. This is why I need to project along UT direction. If I project along UT and I use sum of T equals MAT, I don't have any force along UT. This means that sum of T equals to 0. So no tangential acceleration at this point. So at A, no tangential acceleration. This means that my total acceleration will be just restricted to the normal component, which I already calculated. So A equals to AN, and then my vector acceleration will just have a normal component at point A.
Doctor, because there is no AT, it means it's like a minimum?
Because there is no AT, a minimum about what you are mean? You mean velocity is passing by a minimum?
Yes.
No, velocity is maximum. لأنه at the when you move down, okay, as you go down, the velocity increase. This is a maximum here. For AT equal, yes, you reach a maximum at A, and this is expected because as you move down when you do ski, as you move down, your velocity will increase.
Yes.
Okay. Yeah. Now, if you continue, if the path will continue like this, like let's say, okay, then you will have to move up, and if you move up, your velocity will decrease. This is why you will pass by a maximum at this point. Or you can have a just straight path. If you have a straight path and no friction, so you have a smooth line, then your weight and normal will just cancel out and you will move at constant velocity in this zone. Okay. We projected W on the normal axis, Ali. We projected W, but this is why we put minus 600, because the weight is along the negative UN direction. Okay. Okay, I will repeat. At point A, the normal and weight will not cancel out because A here is a part of a curved motion, not straight motion. So you have a curve, let's say, and in particular, A is one point of this curve. Okay. Whenever you move on a curve, you cannot move on a curve without AN, because when you move on a curve, you should change direction. And to change direction, your acceleration should have a component along the normal. And at point A, what is the normal direction? The normal direction is tangent to the to your path, okay, to UT. So this is your path. UT is tangent to the curve. UN is perpendicular to UT. So you should have to be able to move along this curve. This means from location to another, you are changing in direction. You should have a component of acceleration along UN. And what does this mean? That the net balance of forces along the vertical line here should not be zero, because UN is along the vertical. And because you are moving on a curve, you should satisfy that sum of forces along UN is not zero, is MAN. So whenever you have a curve, this means that AN is not zero. AN is V square over rho. And at point A, rho is not infinity. You are not yet moving on a straight line. You are still moving on a curve. And you can calculate rho at A using this function. Okay. So since rho at A is a finite number, it's 30 meters. This means that when I reach A, when I move just from the point just before just to A, I change direction. And this to do this, I need a normal component for my acceleration. And this normal component is V square over 30. It's not zero. This is why the balance of forces at A will not be zero. And therefore, the net balance should be up because AN is up. And since the weight is downward and NA is upward, NA should be larger than the weight to give me a net force balance along positive UN. Okay. Now, at the instant you move to the straight line path, and in case after A, you have a straight line motion, then in this path, the radius is infinity. And then no normal acceleration because you are not changing direction. Then if you draw the free body diagram of the skier in this part, yes, you can say that the normal will just cancel out the weight. Okay. Any other question? Okay. Now, I will just talk about another scenario that will be a little bit more complex. If they give you a position here, for example, if they give you a position not at A is a particular position because the normal and the weight will be collinear and you don't have any AT. However, if you take any other position as you are moving downward, you will have a tangential and you will have the normal and your weight will not be collinear. Let us take such position. So if I give you any point B here, and I give you the velocity at B, dB given, and I tell you to find what is the normal at B and what is the acceleration at B, what should you do then? Same procedure, but the projections will be a little bit more complex because first step is to draw UNUT at point B. Okay. So if I deal with this point B, then first UT is along the tangent to the path. So this is my UT. UN is along the perpendicular to UT towards the center of curvature. Because you have an upward concavity here, and we verified that the concavity is upward from the second derivative. The second derivative of this equation is positive. So the concavity is up. This means UN should point upwards. So these are my, in this position, these are my UN and UT. Next step, I put external forces acting on my skier. What are the external forces? I have first the weight, and I have the normal. So this is N at B. The normal is always perpendicular to contact. And because here's the contact line is tangent to the path, which is, and the tangent is along UT, this means that the normal is along UN. While for the weight, it's always vertical. So now I presented my forces. As you can see, for the normal, I don't have a problem. It's along UN. However, for the weight can be decomposed into two components, one along UN, one along UT. Okay? Now, who can tell me how can I project the weight? I need to find the angle. How can I find the angle between the weight and UT here? How can I find this angle? What should I do to find this angle here?
From the slope, we can derive it.
Yes, very good. If we find just the slope, when you find the slope of this, your tangent line, this will give you this angle here. This is theta. Okay. So once you find the slope, you say that the weight is doing with UT an angle of 90 minus theta. So this will allow you to project your weight along UT and UN. So you say that I can find theta from tan minus 1 of dy by dx at point B. So already we derived we derived what is dy by dx. We just have to replace x of b. So we know that the derivative is x over 30. So theta is tangent minus 1 of x of b over 30. For example, let me give you that xb. If I give you that xb is 30, for example. So let's say if xb is 30, and if you replace, you get 30 over 30, which is 1. So it's tangent minus 1 xb over 30. For the particular case where xb is 30, then the angle will be 45. So I can say that theta is 45. And I can calculate theta for any position given. They just have to give me xb, I replace it, I get theta. Now we'll put the projection general function of theta. So whenever I find theta, I move to apply my equations. So first I say sum of forces along the normal is equal at point B is equal to the mass times the normal acceleration at B. Now, if I project along a UB, what do I get? What are my projections along UB? Sorry, along UN, I mean. You have the normal. The normal is along UN. So, and it's a positive along the positive direction of UN. And for the weight, since the weight is doing an angle of 90 minus theta with UT, then it will do with UN an angle of theta. When I project the weight on UN, I do cosine theta. When I project the weight on UT, I do sine theta. And because I have the velocity at point B, I can say that sum of forces along UB is just equal to m times VB square. This is in the normal direction over radius of curvature at B. I can get the radius of curvature at B from the formula. So I can calculate completely this term. And this term is equal to NB minus the weight, which is mg times cosine of theta. So in this equation, so only unknown is the normal reaction at B. I can get the value of NB. Once I am done with NB, I still need to determine what is the acceleration at point B. Already I calculated AN as VB squared over rho B. I still have to get the tangential acceleration. And of course, here it will not be 0 because under the effect of weight, when I move down, the weight will help me to accelerate my motion. And I can find what is AT by just writing sum FT equals to MAT. And now if you project along UT, already the normal has no projection. You just have the projection of the weight. And as we said, if you project, you have the weight has negative projection on UN, but positive projection along UT. So plus mg sine theta equals to MAT. And now if you simplify M, you get that your tangential acceleration AT is equal to G sine theta. And you can verify again your result at A, because at A, theta was 0 and sine of theta is 0. So AT is G sine theta, and AN, you already calculated, it's VB squared over rho B. So now you can do the radical to find the magnitude, and also you know how to find the direction. We did together a lot of examples. Once you know the components, you can find the magnitude and direction of your acceleration at point P. Okay, any questions?
It's clear, Professor.
Is AT equal to d theta of V with respect to, I didn't understand the question. Hashim, can you please repeat? D theta of V with respect to I over dt? What do you mean by this? So I will just try to write it. You mean AT, change of direction of V vector with respect to x-axis. Okay. You mean that AT is change of V. You mean dvx by dx? This is what you mean? Look, هي the idea هو no d theta of V. Look, d theta of V with respect to x. Yes, because look, here the idea is that you can say that dy by dx is tan of theta. Okay, and you have that the velocity Vx is dx by dt. Okay, and you can formulate it in another way if you want. You can say that if I consider if I derive tan of theta, if I divide tan of theta by dx by dt, I get the following. I get that dy over dt. So if I multiply dy by dx by Vx, I get tan of theta over dt. So I can say that replacing here dx by dt, I can say that the velocity component of y represent tan theta over dt, but not exactly, and it's related if you want to the variation of theta, but I was not able to derive it directly as d theta with respect to time. I can try to make a relation of variation of theta with t with the velocity. I can try to do it, but here the idea is that you have tan minus 1 involved also. You have that, you can write that tan theta can be written also as Vy over Vx. This is another way to get your variation of theta, because if you divide both sides by dt, if you divide dy by dt and dx by dt, you get that tan theta is Vy over Vx. So the change of theta will be depending, if you want, on the change of velocity of the components of velocity y and x. Okay. Okay. Any other question? Okay, thank you. Bye bye.